Good morning, happy Friday. Today we will continue our discussion of binary for like 2 minutes. And then we will talk about how binary digits are calculated and what the semiconductor device is and how we, that is the transistor, the switch, if you will, that is used in a microprocessor. And then we'll spend the rest of the class talking about microfabrication, nanofabrication, how these things are made using photolithography, from how the silicon is processed to how the patterning of the circuits is actually done. So just to finish up, that's interesting. It's like a funeral pyre. Behold. Maybe someday I'll write on this with permanent chalk. So we're not going to go into too much detail on this, but I just want to show you the simplest possible connection between binary arithmetic and the logic gates that we learned about, and how you construct logic gates from circuits, how you make circuits from transistors, which we'll talk about next, and then how you make the transistors. So while we won't be going into depth on any of this, I just want you to know that in principle, this is how computation works all the way down to the material science, from the binary arithmetic all the way down to microfabrication. So suppose we want to add 0 and 0, 0 and 1, 1 and 0, and 1 and 1. Can you believe that this is college and this is on the board? 0 and 0 is 0. 0 and 1 is 1. 1 and 0 also 1. But 1 plus 1, no. Binary doesn't recognize the symbols in the decimal system. It only knows 0 and 1. So how do you represent what we in our planet would call 2? 1, 0. So the truth table, and this is called the carry out digit. Like what you do with your trash at a national park. So if we have the truth table for the addition, A, B, and Q, which is the least significant digit, the one all the way to the right, and then we have the carry out digit. We draw our normal truth table input 0, 0, 0, 1, 1, 0, and 1, 1. Our Q is 0, 1, 1, 0. And our carryout is 0, 0, 0, 1. Now, if we look at the Q and the carryout columns, we see that they actually match some of the logic gates, two of the logic gates that we talked about on Wednesday. So Q is, anyone remember what this logic is? XOR, which is exclusive OR. So you only get a 1 if it's just OR over here. If there's something that looks like it might be an AND, it doesn't count. Only the ORs get the 1s. So this is either XOR or XOR. A Klingon name, perhaps. The carryout digit, 0001. How about this one? And. So if we have an XOR gate and an AND gate, then we can add two digits together. So we have been drawing these sort of elementary circuit diagrams with switches and a battery and a light bulb, where the switch on was a 1 and the light bulb on was a 1, and we arranged them in series and parallel in order to get the truth tables for all the logic gates. But we can't go in there into a computer, into all the billion transistors that are on a microprocessor with tweezers, and flip switches every time we want to do a computation, or every time we want to turn a pixel and exact a particular color. So we need something electronically. We need switches to control other switches. We need to have voltages that when applied to a switch called a transistor, the current is allowed to flow. And then in combinations, we can do these computations with billions of transistors. So this is what we have been calling a switch. Really has the symbol in a circuit diagram that looks like this. This is a transistor. But what is the actual material, or what is the actual structure of this device? We have a silicon substrate, and this is just going to be the most basic possible archetypal device. And we have two contact pads. Let's say they are aluminum. Could be other metals, but let's say aluminum because it doesn't contaminate the silicon. We call this the source. We call this the drain. And the most important part, highly arguable, but this is an oxide. And in this case, usually silicon dioxide. It's usually an oxide that's grown thermally from the parent wafer. And then we have another electrode on top, which we call the gate. So the oxide is the gate dielectric. And together, this thing is called a metal oxide semiconductor field effect transistor, or MOSFET. And the MOSFET is like a brain cell in a computer. It's what is the basis of all computation. It's the basis of how memory is stored combined with capacitors. It's the basis of all digital computation. Now, how does it work? There are many different modalities in which a MOSFET works. And I won't go into them in detail, but what happens is that a gate voltage above some threshold voltage is applied, which either allows current to flow from the source to the drain or prevents current from flowing from source to the drain. So, so what this is an electronically controlled switch, and the gate voltage is actually controlled by the outputs of other transistors in the integrated circuit. If basically what we're doing is we are creating a conductive channel under the gate dielectric. So this is the channel. And the channel, the charge carriers in the channel have the opposite charge to the voltage applied to the gate, because it capacitively couples through the gate dielectric into the semiconductor. So channel charge carriers have the opposite sign to the gate voltage. And in Nano 104, you will learn about all aspects of operations of MOSFETs. But in our class, I want to teach you how we make these. Is anybody familiar with the concept of embodied energy or carbon footprint? So the amount of energy that it takes to produce some manufactured product. It turns out that in order to make a very low entropy system like a microprocessor, where you have billions of transistors in a square millimeter, a couple square millimeters, something on the order of a square millimeter area, that takes 50 steps to make, like 50 manufacturing steps to make, with an allowable error rate of 1 error in 10 to the 18. Otherwise, the chip is crap. It turns out that a microprocessor has an enormous embodied energy, or carbon footprint, if you made the energy by burning natural gas and fossil fuels, which chances are you did, or one did, not you, the royal you. And there was a paper a few years ago by Eric D. Williams at Arizona State University called the 1.7 kilogram microchip. And now a microchip obviously doesn't weigh 1.7 kilograms, but he did an analysis on a processor, on a DRAM chip, which in this paper is, okay, it's kind of old, it's like 15 years old, but the calculations still hold more or less true. They did these calculations on a 32 megabyte RAM chip, which back then was a lot, and found that if you add up all of the inputs in energy and fossil fuels, it took 1.7 kilograms of stuff to produce a memory chip that's this big. Moreover, if you look at the life cycle of a computer chip compared to other manufactured products, the cradle to grave energy usage of a microchip is much higher in its birth phase than in its lifetime. So you need to have a RAM chip for 3 years in order for it to consume as much energy as it costs to create it. Whereas for a car, the car uses so much more energy, the life cycle profile of energy use is much different. It's on the order of weeks or months, depending on how much you drive the car. Same thing with a refrigerator and other kind of high energy products. A toaster would probably be really intensive or a hair dryer in the use phase, because all you have in there is a resistive heating element, but it burns like a kilowatt, a toaster or a hair dryer. So you'll use up most of the production energy in the first probably few minutes or like an hour of use of an electric oven. Microprocessors, though, totally different. They're designed to be energy efficient, but they have this very low entropy state that took a lot of energy to produce them. And really, the energy story starts with the production of the silicon itself. So if we consider the steps in silicon wafer manufacturing, start with sand, some silicate rocks, and this is SiO2. It's not going to be pure SiO2, although silicon is the second most abundant element in the Earth's crust, followed by, or the first is actually oxygen. But you're not going to have just silicates and rocks and sand. You're going to have carbonates and all kinds of other minerals and stuff. But so you take this silicon ore and you extract the metal from it, or the metalloid in the case of silicon, the same way that you extract metal from other metal ores through a process known as smelting, which is basically a reduction at high temperature over coal or charcoal. And out of this process, so you get a big smelting furnace, and you just heat the hell out of it in the presence of coal. You oxidize the coal, and the metal, or metalloid in the case of silicon, is now liberated at 98.5 to 99% purity. And off of this process comes the slag, which is like the poop. Other minerals and oxides and stuff that are used in, say, construction applications like concrete manufacturing. So now that you have the silicon, it's not pure enough. I've said you can have only one error in 10 to the 18 transistors. Now that refers to the the patterning steps. But in the individual transistors, which are only like 100 atoms across, this is not going to be good enough, right? This is not going to be even close to good enough. So what is done is it's reacted with chlorine to make two liquids, or two small molecules, two volatile small molecules. Silicon tetrachloride and trichlorohydrosilane. And what you do now is distill it. Literally distill it, which is a very useful purification process. And then you react it with with H2, and you get, you're back to silicon now, plus HCl, which is junk, or rather the byproduct, and you get, this now is less than 0.5 parts per billion impurity. This is technically in the form of polysilicon. Which is short for polycrystalline silicon. So instead of a single crystal of silicon, we have different crystalline grains that make up this material. We take this and we melt it. I'll draw the melting over here. Is this an energy-intensive process? Yes, quite energy-intensive, rather energy-intensive. This polysilicon is already about 10 gigajoules per kilogram. Between 1 and 10 gigajoules per kilogram in the gigajoule per kilogram regime. A gigajoule is the amount of energy that goes through the Hoover Dam in a second. So a second doesn't seem like a long time, but that's a damn lot of water going through the Hoover Dam. If you look at one side of Lake Mead and it's up here, you know, practically up here, and then you look at it from the other side and it's down here, and that water is just tearing through the turbines. 1 second gives you enough for, take the liter for 2 amounts of silicon this size, less than 2 amounts of silicon this size. Polysilicon. And we haven't melted it yet, yeah.
How many transistors do we have?
It depends on, out of a kilogram? Oh, I'm not good at arithmetic. It's more than a few. So you might, maybe a chip weighs a few milligrams, like 10 milligrams, but the rest of this process is not going to be very efficient either, especially when we have to literally saw the wafers and then polish them. Okay, so we now melt it. So this is our molten silicon. And what we do is we take a popsicle stick, just kidding, take a stick with a seed crystal on it. And in a process called the Czochralski process, which is spelled in a very intuitive way, named after Dr. Process, you pull the silicon atoms nucleate at the crystal facets, and when you pull this thing out, you get a single crystalline ingot or boule of material. and this is a single crystal. Which means it has almost perfect ordering of its atoms from one side to the other. However, part per billion, still not good enough. Still not good enough. So what it is then done is a process called zone refining, or float zone refining, or the float zone method, where you take a heating element and you encircle the pool of silicon, and you take this heating element and you heat it up past the melting point of silicon, and you slowly raise the heating element with respect to the silicon ingot. And what happens is that the impurities, so it's always locally melted in the vicinity of the heating element. So the impurities are more soluble in the molten silicon than they are in the solid silicon. So what happens is, as this is passed up to the top slowly, the impurities stay melted in the melted part, and they travel up with the heating element. So then all the impurities get concentrated at the top, which is then hacked off with a sword. The next part seriously does involve a cutting process. You then take this boule and you slice it like salami. And so this is the slicing process. You use a very powerful, thin dicing blade that has diamond dust and eye of newt. And these are the wafers. And there's a lot of waste in this process because there's a lot of silicon dust that you get through the actual sawing process. And depending on the size of the boule you start out with, this could be anywhere from 2 inches in diameter to more than a foot in diameter. Forget SI units. Okay, so now we take the individual wafers and we polish them through something called chemical mechanical polishing. Or CMP, which involves abrasive nanoparticles, silicon or other things that are literally used to polish the surface of the silicon. And this is actually quite an active area of research within nanoengineering itself. So getting the reactivity and the abrasivity and the size of the particles right. This is actually a big business. And then what you do is you have now a shiny silicon wafer, and this could be anywhere from 100 microns thick to 1 millimeter thick. Probably some exceptions, but in general, this is what it's going to be. And then you put this in a furnace of like 1,000 degrees Celsius. So this is the thermal oxide growth. And the oxide will grow in air or in a pure oxygen environment, but in air actually works fine in the lab. And this will grow, somewhere in the order of 1,000 degrees Celsius. So now you have a wafer that's SiO2 on the top, and I'll just indicate the thickness. This had a thickness too, but it was all silicon. Now the substrate is silicon, but the top layer is SiO2. Now the SiO2 layer is somewhere like on the order of 100 or 200 nanometers. Then what? There really ought to be a how things are made episode on this. It's basically a plumbus. As you watch more and more nerdy TV shows, you get more and more jokes. That's a little Rick and Morty. Okay, photoresist, spin coating is the only step here. So now you have, I'm going to draw this thicker because I have to add layers to it, sorry. It's really the same thickness. Now you have silicon, silicon dioxide, and then on top of this, you have a thin film of photoresist, which we will abbreviate PR. What is photoresist? Photoresist is the basis of nanofabrication engineering. Photoresist is a photosensitive polymer that either becomes soluble when it's exposed to light. There are two types, positive photoresist and negative photoresist. Positive becomes soluble when it's exposed to light. We'll just say soluble when H nu, and negative becomes insoluble when exposed to light. This process here is called spin coating. Spin coating. Spin coating is how you apply thin films of polymers. You take a solution of the polymer or a neat melt of the polymer, and you put it on a wafer that's on a vacuum chuck, and the vacuum chuck sucks the wafer down to it so that it can't move. And then you pour the photoresist on in a factory. A machine does this, of course. And then it spins at on the order of 1,000 or more RPM. And as the excess material is ejected from the spinning wafer, this thins out. The photoresist film or the polymer film or whatever film thins out, and the longer you have it spinning, the thinner this gets. You can also, if you have a solution of polymer that solidifies, if all the solvent is gone, then the faster the solvent evaporates, the thicker the film is, and then stuff stops being ejected as soon as all the solvent is evaporated. But in either case, either spinning a neat film or a neat solution of, or a neat melt of a viscous material in one hand, where the material you're spinning is pure, or you're spinning a solution of the material in a solvent, it works they both have the effect of giving you a completely uniform film up until the very edges, where you have usually a little bit thicker region called an edge bead, and those regions are usually not usable yet. So a neat solution like neat bourbon, or where there's no solvent, no ice cubes. Okay, now we have silicon, SiO2, photoresist. The photoresist film is also on the order roughly of 100 nanometers, but it could really be anything depending on what you need it for. Sometimes you need the topography of the photoresist film in order to, for example, stamp devices like in an optical storage media. Like if you're storing your data in an optical disc, you need to stamp it using something that has some height to it. And we have the rest of today and all of Monday to talk about this stuff. So if a step goes by too fast, we will repeat it 2 or 3 more times. This can really be anything, 10 nanometers to 100 microns or more, depending on what you need it for. Wow, I'm rather proud of this. I got to use the word smelting in class today in real materials engineering. Okay, so now we're going to switch from these sort of cartoonish 3D renderings of wafers to just what's happening in cross-section on the nano scale. So now we have Si, SiO2, and photoresist. Now, of course, the silicon is much thicker than I've drawn it here. This is 100 nanometers-ish, and this could be 100 microns. This would really go down into the depths of Hades, but I'm not going to draw it that way. And what you do is you expose the photoresist using a mask, and you shine light from some light source made by the Cymer Corporation, which was a UCSD thesis project of the inventor. And this is light. This is called a photomask. This is quartz. So it's single crystal silicon dioxide. And then this piece that blocks out the light is a metal. Usually it's chromium. And this thickness could be anywhere from 10 nanometers to a millimeter for this width. So the line width of the features, this is the cross section, this is the line width. I noticed in the videos that I can't see anything that I write too close to the light because it kind of bleaches out. Okay, so the photomask comes in, it exposes the photoresist, and then what do we have? Is regions here that have now become soluble, because this is a positive photoresist in most circumstances. And by positive, I mean that the transparent regions of the mask ultimately become the transparent or missing regions of the photoresist film. So the pattern in the mask equals the pattern in the photoresist film. So these are now the exposed soluble regions. Then you use a solvent. Then you etch the silicon dioxide with a fluoride source. The reason this works is because fluorine and silicon form the strongest chemical bond, strongest single chemical bond in all of nature, followed by tin bromine. Who'd have thought? But it's true. And HF, which is very dangerous, so consult your doctor before doing this. Etches the silicon dioxide under the photoresist film. If you leave it in there too long, it will undercut the photoresist film, and you don't want that. So you do it for a certain amount of time. You can also do this by vapor phase, reactive ion etching, which is a dry process that will do the same thing. Every step that I'm showing, there are multiple ways to accomplish the same thing, but these are sort of the general ways that give you an idea of how the process works. So I don't want you to go to your job at Intel and they tell you to do it a certain way and say, oh, I learned that it's not that way. Okay, then you do the photoresist stripping. And this could be either a solvent, so i.e. solvent or plasma. And the plasma process, this would be an oxygen plasma etch, which etches organic materials and turns it into CO2. It's like combustion. Gives you the same products as combustion, but it's much more gentle. Okay, so now you have the now you have the SiO2 and the Si. And what we're going to do is spin coat more photoresist. Then I'm going to skip the masking step just for the sake of clarity. We're going to do another step of, oh yeah, I forgot the most important thing was to name this. This process is called photolithography. Which means writing in stone with light. So then we're going to do another photo in 5 minutes or less. We're going to do another photolithography step. of these, so this is the photolithography step and the etching, and the dissolution of the exposed regions of the photoresist. So I skipped a couple steps here. So skip the photolith and the dissolution of exposed photoresist. So now we're getting very close to the MOSFET structure, right? Now we are going to evaporate metal. Like aluminum. So here's our silicon SiO2 photoresist film, and now we have a thin film of metal that we're going to use to coat the whole thing. And we're going to put this in the oven. And I got one already prepared for you. It's all nice and bubbly. This is a metal film. Now we strip the photoresist again. And this is called the lift-off process. Lift off the PR and the metal on the PR. And the final structure that you are left with is the metal oxide semiconductor field effect transistor. Source, drain, gate. And we're done. So starting with sand, we've now made the basis of a logic circuit with which we can do binary logic, with which we can now sample digital signals and upload them to iTunes. And I'll see you on Monday when I'll do a PowerPoint to show you some of the pictures that go along with all of this stuff. Thank you.